SpaceX continues to make rapid progress on its Starship program, pushing forward despite the challenges encountered during Flight 7. Within just 3 weeks of the incident, the company identified and addressed the design flaws that led to the explosion, and is now preparing to test those improvements. Meanwhile, construction of the second launch pad is advancing steadily at Starbase. Let's take a closer look at these key developments. While the Flight 7 anomaly remains under investigation, preparations for Flight 8 are moving forward at an impressive pace. The vehicles assigned for this mission, Starship 34 and Booster 15, have successfully completed cryogenic proof testing, and engine installation is ongoing to prepare them for static fire tests. Post-Flight 7 inspection and repair work at the launch pad is nearly complete, as recent purge tests of the quick disconnect mechanisms indicate the launch mount is back in operation. Soon Booster 15 will be rolled out to the pad for static fire. In an exciting development, SpaceX recently submitted an application to the FCC for Special Temporary Authority, which is required for telemetry and communications during Starship Flight-8. The application explicitly mentions Flight 8 and lists February 24 as the operational start date, signaling that SpaceX is targeting this date for the launch. This aligns with Elon Musk's earlier statement following Flight 7, in which he predicted that Starship would be ready for its next test as early as February. However, despite this target, the actual launch timing remains uncertain. At present, the Starship fleet remains grounded while the FAA conducts a comprehensive review of the Flight 7 incident. Per standard protocol, SpaceX must address the FAA findings and implement any recommended design modifications, procedural changes, or additional safety measures before receiving clearance to proceed with the next test. Given these factors, a February launch appears increasingly unlikely, even if the vehicles and launch pad are ready. The FCC filing suggests that SpaceX intends to launch Flight 8 as soon as regulatory approval is granted, with February 24 serving as an internal readiness milestone rather than a confirmed launch date. More details on the situation are expected to emerge in the coming weeks. Within 3 weeks of the Flight 7 anomaly, SpaceX implemented key design fixes to the Starship system and is now ready to test and validate those improvements. Following the Flight 7 anomaly, SpaceX identified the root cause of the failure as a propellant leak within the cavity above the engine firewall. The most probable source of the leak was the transfer tube which transports propellant from the tanks to the engines. This leak ultimately led to a fire, which escalated into an explosion. To mitigate such failures in future flights, SpaceX has proposed several corrective measures, such as enhancing leak detection systems to identify propellant seepage early, implementing fire suppression mechanisms in high-risk areas, and improving venting capacity to prevent hazardous pressure buildups. It looks like work is in progress to assess and implement these design improvements in future prototypes. A dedicated test article, designated Test Tank 16, was moved into the Star Factory just 1 week after the anomaly, where it received numerous upgrades aimed at addressing the failure points observed during Flight 7. Constructed from a 5-ring forward section with integrated stringers and a 4-ring aft section, Test Tank 16 incorporates design features that align with the latest Starship Block II vehicles, as first seen on Ship 33. Last year, before Ship 33's assembly began, this tank underwent structural testing in a specialized test rig at Massey's. This rig is designed to simulate the dynamic loads and compressive forces that a Starship will experience during flight, with a particular focus on the aft dome. These tests are crucial for verifying the ship's ability to withstand the extreme stresses of launch and flight without failure. The data gathered from these tests played a key role in refining Ship 33's design for Flight 7. However, the anomaly observed during Flight 7 highlights the need for additional design improvements on future prototypes. SpaceX's decision to retrieve the test tank from its storage location after Flight 7 and transport it to the Star Factory strongly suggests that the tank has undergone design modifications over the past 2 weeks. These changes are likely in line with the recommendations SpaceX outlined to address the failure points identified after the Flight 7 anomaly. After receiving the targeted upgrades, Test Tank 16 was transferred to the Massey test site on February 4 for evaluation. The forthcoming test campaign is expected to yield crucial data on whether the implemented fixes effectively prevent propellant leakage under simulated flight conditions, or if additional modifications are required. Should the tests confirm the efficacy of these enhancements, SpaceX plans to incorporate the design improvements into Ship 34 and future prototypes. Otherwise, further refinements will be made on Test Tank 16 and retested before being deployed in operational vehicles. SpaceX's second orbital launch pad at Starbase has advanced significantly in the past weeks. Tower 2 received its chopstick arm assembly just 1 week ago, and teams are now focused on bringing the system into full operation. The cable reeving process has commenced, which involves threading the cable through a series of pulleys and sheaves installed on the tower. This setup will connect the drawworks mechanism to the chopstick carriage, allowing for precise control of the chopstick's vertical motion. The system ensures that the cable can be properly managed and tensions can be adjusted as needed to achieve smooth, reliable movement of the chopstick arms. The traveling block, installed on the carriage a few days ago, serves as a critical component in guiding the cable as it moves with the carriage. The cable will be reeved through the traveling block, which helps distribute the load and allows for controlled motion. After passing through the traveling block, the cable runs back up to the top of the tower, where it is securely anchored to an attachment point. This anchoring mechanism allows for precise tensioning, ensuring the chopstick arms move smoothly and accurately. We can expect the chopstick to be operational in the coming weeks, assuming the ongoing work is completed as planned. However, before the arms are used for rocket stacking or catching activities, SpaceX will conduct a series of validation tests to ensure everything is ready for operation. These will include a range of movements, such as opening and closing cycles, to verify proper hinge operation and synchronization between the arms. The arms will also be moved to their highest position and tested repeatedly to ensure reliable operation. To assess structural integrity and load handling capability, engineers are expected to perform load tests using water bags, simulating the forces the arms will endure during rocket stacking and catching operations. In parallel with the efforts to bring the arms into operation, progress on the Pad B flame trench is advancing smoothly. Excavation is nearing completion, with excess concrete removed from the piles. Installation of pipes and conduits for both propellants and electrical power is underway, and concrete work has also begun. To meet Pad B's operational needs, the existing tank farm is being expanded by installing new propellant storage tanks, pumps, heat exchangers, and other associated components. Meanwhile, at the Sanchez site, the construction of the Pad B launch mount is making steady progress. Welding operations continue to secure the individual components of the mount, while plumbing work is also progressing. However, several key installations are still pending, including the booster hold-down clamps and the outer 20 booster quick disconnect mechanisms. The launch mount will feature a double-bucket flame diverter beneath it, designed to redirect exhaust gases generated by the booster engines during ignition. This system is vital for protecting surrounding infrastructure from the extreme thermal and acoustic effects generated during launch. The diverter will consist of a robust steel framework made of pipes that channel water through internal passages. When exhaust gases are diverted, water will be sprayed through small perforations in the pipes, effectively absorbing both heat and noise. The main water supply manifolds, responsible for distributing water to the diverter's spray channels, have already been installed onto the framework. Currently, individual water pipes are being positioned over the framework to complete the basic structure of the flame diverter buckets. Once the flame trench work is completed, the launch mount and flame diverter system will be integrated and installed. With the current pace of progress, Pad B is expected to be fully operational by mid-2025. At the production site, the assembly of Starship 35 was completed this past week with the installation of the aft dome section. The next steps include adding the aft flaps, electrical and hydraulic systems, and other critical components, with the engines to be installed last. Starship 35 is slated for Flight 9 and will be paired with Booster 16, which has already been fully stacked. Preparations for cryo-proof testing of Booster 16 are currently underway. Meanwhile, construction continues on sections for future Starship and Booster variants, which are expected to be completed and stacked in the coming weeks and months, ensuring continued progress toward upcoming missions. Now, let's discuss the latest updates from the world of science and technology. Blue Origin's NS-29 mission, launched on February 4th, marked a significant milestone in lunar technology testing. The uncrewed flight lifted off from Launch Site 1 in West Texas, following a 1-week delay caused by adverse weather and an avionics issue. At 2 minutes and 30 seconds into flight, the first stage booster successfully separated from the crew capsule and began its journey back to Earth. The booster then executed a precise vertical landing on the landing pad situated about 3.2 kilometers north of the launch site. Meanwhile, the capsule continued its ascent and reached a maximum altitude of 105 kilometers above sea level, experiencing approximately 4 minutes of microgravity during its suborbital trajectory. The mission carried 30 experimental payloads, including several designed to operate in a simulated lunar gravity environment inside the capsule. To achieve this, New Shepard employed an innovative spinning maneuver using its reaction control system thrusters, rotating the capsule at 11 revolutions per minute, generated centrifugal forces replicating lunar gravity for approximately 2 minutes. One of the most critical experiments aboard was NASA's Lunar Chi Combustion Investigation, or LUCI, which analyzed flame propagation patterns in simulated lunar gravity. By observing methane combustion in a controlled chamber during the low-gravity phase, researchers aimed to improve fire safety systems for future lunar habitats. This experiment's results could fundamentally alter material selection and ventilation designs for Artemis program bases. In other key study, the electrostatic dust lofting experiment examined how lunar regolith particles gain electrostatic charge when exposed to ultraviolet radiation. Understanding this effect is vital, as charged dust can adhere to spacecraft surfaces, pose operational hazards, and degrade equipment over time. Additionally, the fluidic operations in reduced gravity experiment explored advanced liquid management techniques crucial for life support systems and water resource monitoring on the Moon. Several other experiments on board the mission focused on in situ resource utilization, a critical area for sustainable lunar exploration. Additionally, the mission included a diverse set of experiments on dust mitigation technologies, advanced sensors and instrumentation for data collection, small spacecraft propulsion tech, and entry, descent, and landing navigation systems. These advancements aim to enhance spacecraft performance, enable efficient resource extraction, and improve the safety and cost-effectiveness of future space missions. After completing its scientific objectives, the capsule began its descent back to Earth. While one of the 3 main parachutes exhibited delayed inflation during re-entry, the redundant design ensured a safe touchdown in the Texas desert. From launch to landing, the entire mission lasted 10 minutes and 6 seconds. Looking ahead, Blue Origin has confirmed additional New Shepard missions, both crewed and uncrewed, some of which will carry experiments aimed at advancing lunar surface technology for NASA. Thank you for tuning in for the latest science news and Starship updates. If you enjoyed this video, please hit the like button, leave a comment, and share it with your friends. Also, don't forget to subscribe to the channel and turn on notifications so you never miss an episode.